Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So let's continue. We are still on parallel hardware. So what we have discussed earlier, so we have still on the parallel hardware. Okay, we discussed on the von Neumann architecture. Okay, von Neumann machine. So basically you have CPU and you have system bus and then you have memory and you have IO here. Okay. And then we came across, we have do some calculations, some examples on our von Neumann bottleneck. The idea is the CPU is faster than the memory can handle. Okay, the data rate of the memory. Okay, faster than memory or any IO. Okay, the memory is the fastest, and then the IO is even slower, like printer, Ethernet, and so on. Okay. So one of the solution is to have the cache memory. Okay, to have the cache memory. Okay, so the cache memory, instead of if you have, for example, 1,000 matrix element, one array which is content of 1,000 elements. Then we have the cache is reside between the CPU and the main memory. Okay, so rather than you go directly CPU to memory, but in here on the first scenario, and this is second scenario, on the first scenario you just read one by one. Okay, so A0, A1, so you just read A0, comma, then A1, comma. Remember that once instruction to fetch the memory is take a long time. Okay, compared to the processor speed, as we have seen in the calculation. Okay, so that's why we use the cache memory because of the principle of locality. Okay, so this is the principle of locality, which means that most probably you will need the data closer in the data or instruction closer in time and closer in space. So like this one, you probably will need A0 to A0, A1, A2, and A10 for A9, for example. Then you read directly A0 until A9. Okay, so you can see the one block directly. Okay, rather than one element you read it in one block. Okay, so that's why it depends on the cache memory. Okay, but there is an issue on the cache as well. So we have cache hit and we have cache miss. Okay, cache hit means that the data that you required is already on the memory. Okay, on the cache memory. Cache miss means the data that you required is not on the main memory, so you need to load again from the main memory. Okay, you need to load again from the data from the main memory. Okay, and of course, cache is limited. Remember on the pyramid here, the memory hierarchy. So the fastest is registers, CPU registers. Okay, it's closer to the CPU, and then we have the L1 cache, L2 cache, L3 cache if you are using multi-cores, and then we have the main memory. Okay, so you can see several steps here. Okay, you might have cache miss on L1, but you must have you might have cache hit on L2. So that's okay. So you can load to L1. But remember the size is smaller. Okay, L1 maybe 512 kilobyte, L2 maybe 2 megabyte, L3 maybe I'm not sure. I think 16 megabyte and so on. Okay, but it's limited, very small compared to the main memory, which can range to 32 and 32 gigabytes, 64 gigabytes, and so on. Okay, so very small. Okay, so this is the cache miss, and this is the structure of the cache. So you do here on the block transfer here, and then you read the data one by one here from the cache memory. Okay, if you have various cache, then you can do also read here, and then read here, and then read here. Okay. So again, the principle of locality. Most probably you will need the data closer in time and closer in space. Okay, so you can see here, this is the block. Okay, of course you have the line number here. Okay, so you are reading in the block here. This size is the same like this size. Okay, so you have one block directly. Okay, you have line number here and memory address. So for example, 0, 1, 2, 3. So you have until this block, for example, 10. So you have 0, 1, 2, 3 until 10 here. Okay, you read all the content here. Okay, so you read this one in one go. Okay, and the next block, and the next block, and the next block. Okay, as it is required. Okay. Okay, so let's move on. What are the issue with cache? Yeah, so and when the CPU attempts to read data or instruction, remember that the cache is not only in data, but it can be an instruction. Okay, instructions can be put in the cache. That's why an L1 cache, there are two types on the L1 cache. We have the cache for data and cache for instruction. Okay, so yeah, so if there is a cache read, if a cache miss, mean that the data is not available. So it will read from the memory the cache line that contains the need information and store it in the cache. Okay, so this may stall the processors because it's not available. Okay, so you need to read. So the CPU will see in the cache. Okay, if it is not there, okay, then it will read from memory. Then you can see, you go back here, you go back here, you can see the cycle that it needs. Okay. And then when a CPU writes data to cache, the value in cache may be inconsistent. Reading is okay because you don't change anything. Okay, reading is fine. But whenever you have writing, okay, there's come the problem. Okay, so for example, I've already updated x equal to 2 here, and the memory here x equal to 3. Okay, so which one to use? Okay, so there are two things here. Write through. So whenever you update something, you write x equal to 2, then you go to the memory and write 3. Okay, or you have write back. Write back means you just mark as dirty. Okay, you mark as dirty here. X is dirty. There's some status there. So clean or dirty. Let's have the D status, which is for dirty. If D equal to 1, means that you need to write down here. Okay, you need to write down in the main memory. Okay. Yeah, so the dirty line is written to the memory. Okay. Okay, so another issue will be on the replacement algorithm. Remember here you have cache. What will be the cache size? Okay, because you need to have the trade-off between the cache size and as well as the how many level of cache, cache level. Okay, is it better if you have L1, L2, L3, and then L4, for example, or is too complicated? Okay, because the more level that you have, it will be more complicated. Remember, if you have 3 level, the writing problem persists into 3 level as well. Okay, so if you modify something on L1, you need to pass it back to L2, pass it back to L3, pass it back to the memory. Okay, to the main memory. Okay, and then if the cache is full, then which one is to replace? So you come also here something like replacement algorithm. Okay. Okay, so let's move on. Okay, so another issue in cache design is deciding where lines should be stored. Okay, where lines mean the block of the data should be stored. So this is cache mapping. So there are 3 methods. The first one is full associative, means that a new line can be placed at any location in the cache. Okay, full associative. Okay, so a new line can be placed at any location. Okay, if you have new data, that's random. Okay, depends on the availability. Okay, if line 1 is available, put on line 1. If line 3 is available, put on line 3. So that is full associative. Okay, or you can have also direct map. So each cache line has a unique location in the cache to which it will be assigned. Okay, or you can have n-way set associative. So each cache line can be placed in one of n different location in the cache. So you have, if you have 2-way, so you have set 0 and set 1. If you have a 4-way, you have set 0, 1, 2, 3, and so on. Okay. So yeah, so in 2-way, so each line can be mapped to one of 2 locations. Okay. So when more than one line in memory can be mapped to several different locations in cache, we also need to be able to decide which lines should be replaced or evicted. Okay. So this is the replacement algorithm. Okay, so this is the replacement algorithm. I think there are basically there are 3 types, which is there are 3 algorithms: first in, first out. Okay, first in, then first out. Least recently used, the one that is not used recently, then you can remove. And the other one, I think clock algorithm, because you cannot implement the optimum. So clock algorithm, which is the modification of first in first use. Okay, but I think the cache designer or the CPU designer use this one. This recently used, so there is a timestamp. Okay, if this old enough, then it can be replaced. Old enough means it will not be used in the near future. Okay, in the far future maybe, but in the near future, hopefully it will not be used. Okay, so just go for prediction. Okay. Okay, so this is the example. Suppose our memory consists of 16 lines representing like 16 gigabyte, for example, which index 0 to 15. So this is 0 to 15. Okay, remember that from here, then you need to map to this one. Okay, and then you have the cache consists of 4 lines with index 0 to 3. Okay, so you have 4 line cache. Okay, line cache here. Okay, and then you can read everything here 4. Okay, every line can have 4. Okay. So the full associatives mean len 0 can be assigned to cache location 0, 1, or 2, or 3, fully association anywhere. Okay. It doesn't matter. So you have 4 cache lines. Okay. You have 4 cache lines 1, 2, 3, 4. 1, 2, 3, 4. Okay. 0, 1, 2, 3. Okay. And then anything that available, you just put it there. Okay. So this is fully associative. Okay. Direct map, you put like this. 0, 0, and 1 to 1, 2, 2, and 3, 3, and then you reset back into zeros, okay? Because you only have four cache lines, okay? And so on, okay? If two-way associative, then you can do like this, 0, 0, or 1, okay? So this is 0 or 1, this is set 0. If 1, and then 2 or 3, so you can see here, if even number, then you put on 0 or 1 cache line. Okay, the 0 or 1 cache line here. Okay, if 1, then odd number, you put 2 or 3. So you are try to distribute the odd and even into the set. Okay, into several set. Okay, of course, if you go to four-way associative, then it will become direct map. Okay, 0, 1, 2, 3. Okay, if you use the four-way associative, it will be like a direct map. Okay. Okay, so if you have any question, feel free to interrupt me. Okay, so let's move on. Yeah, so the
I have a
CPU.
question.
No question. Okay. Oh,
I
you
have
have
a
question?
question.
Okay, so yeah, you can ask.
Yeah. Which cache mapping is faster? Full associative or direct map?
Full associative or direct? It depends. Okay, depend. I haven't done. Of course, we need to do a simulation on this one. Okay, I will try to look at that because you need to find out which one is better. And this method normally implemented in hardware. So I'm not sure which the CPU designer which one that they use. Okay, but you can do some simulation for this one. It depends also on the program. Okay, because some program maybe randomized will be better. Okay, some program maybe some structured will be better. Okay, and some program maybe depends on the program. Yeah. Okay. I'll get back to you if I have more information on this one. Okay, especially on the CPU design. Okay.
Okay.
Okay. So yeah, because like this, the CPU, the working of CPU cache are controlled by the system hardware, which is the memory management unit in CPU. Okay, in CPU here you have memory management unit. It will manage all the things, including that one, the implementation of replacement algorithm, whether first in first out, least recently used, or clock algorithm. Okay, or which is it fully associative, direct mapping, or n-way associative. Okay, so it depends on the CPU designer. For us, it's transparent. Okay, we don't see. So the programmers do not directly determine which data and which instruction are in the cache. Okay, so it is handled by the MMU. Okay. But knowing the principle of spatial and temporal locality allows us to have some indirect control. So remember, this one is indirect control over caching. Yeah. So for example, we have two-dimensional arrays in row major order. So the memory is effectively a huge one-dimensional array. So the memory is like this, right? So this is the memory. Okay. How do you find? How can you allocate two-dimensional array. For example, you have a 10/10. Okay, so you just have like this 10 until 10 times. Okay, 10 times. Okay, so if you have a to 10, for example, this one starting in here. Okay, and a to 10. Oh, sorry, this one, the last position. A2, this is 1, 2, 2, and then 10. Okay. Sorry, in C like, then it will be like 0, 1, and 2 here. Yeah, in this place. Okay, 2, 10. Okay, and so on. Yeah. Yeah. So for example here, suppose max is 4. So you have A44, and elements of A are stored in memory as shown in the table. So and A01 is stored immediately after A0, A00. Okay, so you have this one represent the, is it the row? Yeah, the row. Okay, and this one represent the column. Okay, so you are visualizing like this. Okay, so A0, A1, sorry, A0, this is A10. Okay, and you have here and then A01 and continue. Okay, until A04. Okay, so you can see then it's move on to here A10, A11, A12, and A13. Sorry, this is not 4, 3. Okay, so you can see here, if you go, and then you need to visualize that this one will be one big line like this. Okay, one big line, continuous line like this. Okay, in the main memory. Okay, so you can see here it is better if you go like this, and not one, and not one. Okay, and continue. Okay, because it's following the element here, the element of a memory. Okay, rather than you are jumping like this. So for example, you do a not, then you jump to A1 node. Okay, you jump to another location, which is this one, this location. Okay, so you not do like this, 2, 3, but from here, then you jump to here, jump to here. Okay, then after finish, go back to second line here. Okay, so that's why the way that you do the looping also will determine faster. Okay, so we determine whether it's faster because of the catch. Okay, so you can write catch here directly. Okay, you can read this one. Okay, because this is closer in time, closer in space. So you put this on the catch. Okay, you put this on the catch. Okay, if 4 maybe it's not obvious, but you just try. If for example maximum is 1000, then according to the books, the first pair of nested loop, this one, is 3 times faster than the second pair. Okay, but I tried this one, but I have similar things. It's depend on the C compiler as well. Depend on the C compiler. If the C compiler is intelligent enough, although you are writing like this, okay, but it can rewrite like this. Okay. Okay, so let's move on. Yeah, so the cache make it possible. So another von Neumann what you call solution, von Neumann bottleneck solution is to use the virtual memory. Yeah. Okay. So the cache make it possible for the CPU to quickly access instruction and data that are in main memory. However, if we run a large program or a program that access very large data set, all of the instruction and data may not fit into the main memory. Okay. So there's another what you call another a limitation. Okay, of the von Neumann architecture. Okay. So what we have here, we are using now virtual memory. Okay, so we are using virtual memory. So basically like this. Okay, so but the virtual memory need to be supported by CPU. Okay, need to be supported by CPU. Okay, so you allocate this one. This is the main memory. Let's say you have 16 GB, and then you have here the hard drive. Let's say 1 terabyte. Okay, so you can allocate part of your hard drive as the memory. So this is 16 GB, but this one will be your virtual memory. So you are using part of hard drive as the what you call as the you treat it as the main memory. So the CPU will see this one, the memory, and then including the virtual memory. Okay, so instead of only 16 gigabyte, now you have 16 and 16, so altogether you have 32 gigabytes. Okay, so whenever you have you are loading, for example, Adobe Photoshop or Adobe Premiere Pro, so it is okay because now you have a bigger memory than you need. Okay. Okay, so that's the one of the what you call the cache is working if you have the small data set, a small program, but the virtual memory is working whenever you need a you run a very big program like Adobe Photoshop, Adobe Premiere Pro, other video editing software, and so on. Okay. Okay, so yeah, so this is a virtual memory. So you have virtual address. So but remember that this is on the hard drive. So this is slow compared to this one. Okay, but in a way that it does not limit your program. Okay, to 16 gigabyte. Now you can have 32 gigabyte program, or if you allocate more, maybe 48, maybe 64 gigabyte if you allocate more on the virtual memory. But remember that this one is slow. Okay, although you can use this one, but this is slow. Okay, so you need to have the trade-off. Okay, you need to have the trade-off. Okay, so let's move on. So the virtual memory was developed so that main memory can function as a cache for secondary storage. So the previously we have CPU, we have cache, okay, and then we have memory, and then we have hard drive, secondary storage, or SSD. Okay, for example. Okay, so the main memory here become the cache for the hard drive. Okay. The same thing is exploit the principle of spatial and temporal locality. Those parts that are idle are kept in a block of secondary storage called swap space. Okay, so this is the swap space. So means that you have a very big Adobe Photoshop program, for example, it occupy, let's say, 20 gigabyte. Okay, so let's say you can only use 14 gigabyte because 4 gigabyte is used for your OS. Okay, 4 gigabyte is for your OS, and you have 12 gigabyte here you use for Adobe. Okay, but it requires more because the Adobe size may be 16 gigabyte. So you can use this one as 4 gigabyte swap. Means that the function that you are not need yet, you can keep it on the hard drive. Okay, you can keep it on the hard drive. Okay, but whenever it requires, then you can swap this one, swap here, and read into the main memory. Okay. Okay, so like cache virtual memory operates on blocks of data and instruction called page. Previously, we have a block of data. So remember that we have line here, and then we read this one in a block. Okay, and this is put. If you translate this one, become this like this in a cache memory. Okay, this is the main memory. Okay, so similar thing with the virtual memory. We are using the page. Okay, I'll discuss on page later on. Okay, in a moment. Okay, so yeah, so secondary storage can be hundred of thousand or times slower, hundred of thousands slower than memory. Remember that this is like an I/O. Okay, the memory, for example, requires 1 nanosecond. The hard drive requires 1 millisecond, so 1,000 slower or even more. Okay. So most systems have a fixed page size in the range 4 to 16 kilobytes. Yeah. So we may try we may run into trouble if we try to assign physical memory, not means that it is fixed. Okay, so you compile your program and it must run at 1,000 location, for example. Okay, at 1,000 address. So the address is linear for the main memory. So from 0 to your maximum 16 gigabyte, and then you wrote a program that is specifically access the physical address 1,000, for example. Okay, then it will be a problem because you cannot move anywhere. Okay. So when the program is compiled, pages are assigned virtual page number. Then when the program is run, a table is created that maps the virtual page number to physical address. So you have a mapping between the page number to physical address. So it doesn't matter where do you put, okay, not necessarily in 1,000, just so for example, your program one of time you can run in 1,000, program you can 1,000. In the other time, it doesn't matter. You can run in the position of 5,000, for example. Okay, it will behave the same thing. Okay, it will behave the same thing. Okay, So yeah, so you have main memory here, we have program A, program B, program C, so you can allocate anywhere. Okay, actually not necessarily in one continuous here, you can place anywhere. Okay. Okay, I'll explain now about the paging. Okay, what is paging? Okay, the paging and segmentation. I'll skip segmentation for the moment. It need to be supported by CPU. So the modern CPU supported the paging. Okay. So what we have here at the 9050 or 60, for example, you have 64 megabyte. Okay, and then let's say you have divided into 8 fixed size, 1, 2, 3, 4, 5, 6, 7, and 8, for example here. Okay, each one is 8 megabyte, and the first 8 megabyte is used by the OS. Okay, 8 megabyte used by the OS. Okay, and then what happened on the fixed size here, for example, you have program A 7 megabyte, program B 1 megabyte, okay, program C 8 megabyte, program D you have let's say 10 megabyte. Okay, so on program A you can place it here, program A. Okay, but there's some wastage. Okay, so you have some wastage because this is the total is 8, but you are using only 7. Okay, so you have 1 megabyte internal fragmentation. Okay, you have 1 megabyte internal fragmentation. Okay, and B is even worse. Allocated B, and you cannot fix this one. Okay, you cannot fix that one at that time. Whenever you start the program, the OS, it will divide it into the same amount here. Okay, it cannot change. Okay, so this is called fixed partitioning of memory. Okay, so this is fixed partitioning of memory. Okay, and then we have here 8 minus 1, so you have 7 megabyte wastage. Okay, because you only use 1 megabyte and 7 megabyte is waste. It cannot be used by any other program. Okay, it cannot be used by any other program. So the B need to finish first, then it can replace. Okay, and C is nice. So you have 0 wastage. 8 minus 8 is 10. Sorry, 8 minus 0. Okay, no wastage. Okay, no waste, no internal fragmentation. Okay, and the D, what happened to the D? D cannot fit. D cannot fit. Okay, because it is 10 megabyte. Okay, so you can see here you cannot fit this one. And as people move on, so you have what you call now we move on to something like this. Okay, so we have here, for example, user program A. It created a page that is small enough. Okay, let's say previously we have here 8 megabyte. Okay, 64 megabyte, for example. Okay, you divide it into 8. Okay, until 8 here. Okay, so you have 1 until 8 here. Each one is 8 megabyte. Okay, 8 megabyte. Okay, now on the paging, we make it as small as possible. Okay, we make it as small as possible. Let's say we make it 1 megabyte. So instead of 8 slot, now you can have 64 slot. Okay, because you have total is 64 megabyte. Now you divide it into small enough. Okay, small enough slot. Okay, so so previously what happened? If you have 7 megabyte, then nicely fit here 7 megabyte, 1, 2, 3, 4, and 7, for example. You have 8 megabyte nicely fits 8 megabyte. If you have for example program C 1 megabyte, you can occupy 1 megabyte. Okay, and also the other thing is no need to be continuous. Okay, for example, this is occupy. Okay, and then you need program E is 2 megabytes, so you can have E naught is in here. Okay, and E1 is in here because you have page table as your lookup page. Okay, it will record E naught will be on the first location and E1 will be on the fourth location. Okay, so it doesn't matter. Okay, the other things is what happened, for example, if you have program F, which is you have 1.5 megabyte. What will happen? Okay, so you can see here it will occupy two blocks, of course, you will occupy two blocks because you cannot have half page. Okay, so you will occupy two blocks, so altogether 2 megabyte, but your wastage will be smaller. Your wastage will be 0.5 internal fragmentation. Okay, that you cannot use, but that's fine. Okay, that's fine. Okay, so this one 0.5 is also, if you have 2.5, 3.5, 4.5 is the same. So only the last page. Okay, only the last page. For example, you have 4.5, so you need to have 5. Okay, 1, 2, 3, 4, 5. So only the last 5 have the internal fragmentation of 0.5. So you can see the benefit of paging. Okay, and this is supported by the hardware. Okay, and what you call, so it means that it is transparent to the programmer, to the user. Okay, we don't know where they put the paging. Okay, we leave it to the memory management unit of the processors. Okay, so as you can see here, this is the main memory, for example. Okay, it does not need to be continuous because you have the page table that act as the translator on the location between the hard drive and the main memory. Okay, something like this. Okay, so yeah, so the virtual address divided virtual page number and byte offset. Okay, so this is virtual address. You have page number and offset. Okay, so yeah, so it means that it doesn't matter. Okay, so for example like this. Okay, for example, you only, this is 1 megabyte page. Okay, and your program is also 1 megabyte. Okay, so you can put it here on the first one. Okay, and then there's some offset. For example, this is the last instruction that you run. Okay, then there's an offset of, let's say, 100 kilobyte. Okay, it doesn't matter, you can put it here, or you can put here on, let's say this is number 1, 2, 3, 4, or number 4, for example. You can put the same thing as long as you know the starting address. Okay, and then add the offset here, 100 kilobyte. You always point to the same location of your program. Okay, you always find the same location of your program. Okay, so if you suppose that we have 32 bits and our page are 4 kilobyte, which is 409 byte. So if you have 32 bits, means that this is 12 is used for the page. Okay, so and then this one is the offset. Okay, the location. Okay, the location. Yeah, so this is the how do you access the page frame, the paging mechanism. Okay, so find out the page, the page table pointer. Okay, find out the page number. Okay, and then the page number will we see the starting address. So something like this. Okay, you have the page number 1, and then give this starting address. Okay, page number 2, give this starting address, and then you combine the starting address with the frame. So you'll see, you'll have your location here. Okay, you have the actual location on the physical address. Okay. Okay, so let's move on. Any question so far before I move on?
I have another question. If that's
Okay. Yeah.
Does virtual memory work the same way in every operating system?
Yeah, more or less is the same, because remember that in order to be able to use virtual memory, like and also paging and segmentation, you need to have the CPU, the CPU that supported, modern CPU that supported the virtual memory. Okay, so means that maybe the implementation wise is different from OS to OS, but it behaves the same because it's transparent to the OS. Okay, the one that control is this one, memory management unit, which is in the processor itself. Okay.
Okay.
Okay, good question. Okay, so let's move on. We have how many minutes? Okay, let's see. Let's target another 20 minutes, inshallah. Okay, so let's move on. Another solution. Okay, not another solution. Actually, this is still on virtual memory. Okay, but now let's say, because you can see this is the page table. The page table is put also, so you can see like this. If you have main memory, okay, main memory, you need to allocate some here as the page table. Okay, because the page table will link between your program and then your actual location in the main memory. Okay, so you have the page table in here. Okay, so similarly, now the TLB is in essence just putting a cache, but the cache specifically for the page table. Okay, because remember that reading any data from memory is slower. Okay, if you think like the previous one. Okay, reading the data from memory is slower compared to reading the data from or instruction from the cache memory. Okay, so the TLB is the cache. In essence, the TLB translation look aside buffer is the cache for the page table. Okay, so it will be faster. Okay. Yes, using a page table has the potential to significantly increase each program overall runtime because you need to access the page table and you see the location. At least you need to read twice. Okay, the where is it, and then you read the actual one. Okay, the actual program. Okay, so we have a special address translation cache in the processor, which is TLB. So the TLB it will be implemented in the processor. So not only you have L1 cache, L2 cache, L3 cache, so you have also TLB cache. Okay. It catches a small number of entries, typically 16 to 512, from the page tables in the very fast memory in the CPU. Okay, so whenever you have page fault, okay, and yeah, so what's mentioned here is like this. Remember that on the let me draw like this. You have page table. Okay, page table. Okay, say that you have prepared a page table, let's say not too big, like let's say 256 megabyte. Okay, just an example. Okay, page table 256 megabyte, the size. Okay, so what you can do, you can put half, because you want to save the main memory is precious. Okay, because this one is faster compared to the hard drive. Okay, so what you can do, you can allocate also on your virtual memory the page table. Okay, so you divide, for example, half 128 here and 128 here. Okay, but if you see here, you try the processor requested the page. So this 128 is the most used. Okay, for example, you are open Adobe Photoshop. Okay, you open Adobe Photoshop and then you just load the necessary functions. Okay, on your page table here. Okay, it mapped to the necessary function on your page table. Okay, but for example, you have something like special function in your Photoshop. Okay, it is not here. Okay, means that you have page fault. Okay, page fault. Then you need to read here. Okay, this one need to load to here. Okay, so you can see twice, maybe triple time, because you need to check in the page table here, check in the page table here. Then if it's page fault, then you go to the here, and then you need to load, need to replace the page table here. Okay, you need to replace. Okay, whenever you replace means you load the new one and you need to put back here the old one. Okay, put the old one and replace the new one here. Okay, so that's what happened for the page table. Okay, means the page table also occupying inside memory. You don't, for example, you don't want to load the whole thing 256 on your main memory, so just 128 on the main memory, 128 on your virtual memory. Okay, in that case, then you can load other programs better. Okay. Okay, so let's move on. So this is the translation look aside buffer. So basically, this is like cache on your hard drive. So you have virtual address, for example, and then it is there on translation look aside buffer. It's in location. This means that TLB hit. It is there already. So you just generate the output of the frame. Okay. If TLB miss, it's not there on translation look aside buffer, then you need to go to the page table on the main memory. Remember, this is main memory. Okay, if you have page fault, that you need to load from here. Okay, from the virtual memory on the secondary memory here on the hard drive, on the SSD and so on, and then you can load the main the page. Okay. Okay, let's move on. So we have discussed the solution to von Neumann bottlenecks, the cache, and the virtual memory. Okay. Now the another solution for von Neumann bottleneck is this one, instruction level parallelisms. Okay. So the instruction level parallelism attempts to improve processor performance by having multiple processor components or functional units simultaneously executing instruction. Okay. So we try to run two things at the same time. Okay. If you can divide the data, that will be good. Okay. The data parallelism. If you can't divide the data, then there's no point. Okay. And this is working only for example, as you are calculating in a matrix, for example, and you need to multiply by some variables or something, then you can divide the data. Okay. So there are two main approaches to instruction level parallelisms. The first one is pipelining. So functional units are arranged in stages. Okay, and then or you can have multiple issues, means multiple instruction can be simultaneously initiated at the same time. Okay. So yeah, so you have here, for example, I'll get the example. So what is pipelining? Pipelining is like similar to a factory assembly line. So you are trying to making a car, for example, you try to fit the tire. Okay, you fix the engine. Okay, and this one do something. Yeah, this one do some I think painting, for example. Okay, this is painting. Okay, this is the engine. Okay, and this is the tire, put the tire there. Okay, so as you go along here, from here, 1, 2, 3. Okay, if it is finished in here, then it can put in a new car. I can place the tire. Okay, and then while the car from here move to here and put the engine. Okay, and the car have finished here, move here. Okay, and then put the painting here. Okay, so this is like a pipelining. Okay, so for example, like this, suppose that we want to add the floating point numbers. Okay, like this. Okay, we want to add the floating point numbers. Then there are 7 steps. Okay, for adding floating point numbers. Fetch operands. Operand is the operands here. Okay, and compare exponents. Okay, if different, then make it the same. Okay, shift one operand to make it the same. Okay, and add. Okay, then this is the result. Okay, and normalize the result. Okay, to be 1 point something. Okay, 10.5. Round the result only 1.05 and store the result. Okay, this is the last one. Okay, so this is the just adding floating point number. You need to have 7 operations. Okay, you need to have 7 steps of operation. Okay. Okay, so assume each operation takes 1 nanosecond. Okay, then this one will take 7 nanoseconds. Okay, if, for example, you have 1 gigahertz clock CPU clock, for example, then it will take 1 nanoseconds. Okay, each operand. So if you execute the code here, for example, if you execute the code and then the 1000 floating point numbers, okay, 1000 floating point number, and then you just do the adding. We do the loops here 1000 times, then it just multiply by this one. You'll need 7,000 nanoseconds. Okay. And as an alternative, we'll do the pipelining. Okay, as an alternative, we can do pipelining. Okay, so we can divide our floating point adder into 7 separate pieces of hardware or functional units. Okay, the first unit will fetch 2 operand, the second will compare exponent, and third one will receive 1 operand, fourth one add, normalize result, round result, store result. So you have this operation you can have into, previously it is serial like this. Now you do it in pipeline. Okay, one, but you can do this one up to here. Okay, and continue. Okay, you do the pipelining. Okay, so the output of one functional unit is the input to the next. Okay, so next one, next one, next one. Okay, so let's move on. Yeah, so yeah, a single floating point addition will still take 7 nanoseconds because you need to have 7 steps. Okay, similar thing. However, when we execute for the for loop, okay, we can fetch x1, y1 while we are comparing the exponent x0, y0. Means that the x0 or y0 is already on the second stage here, on the second step. Okay, so this one we can fetch the x1 and y1. Okay, and continue. Okay, if x0 and 0 is in here, okay, this one will be x1, Y1, this one will be X2, Y2, and so on. Okay. So it is possible for us to simultaneously execute 7 different stages in 7 different editions. Okay, so from the next table, we see that after time 5, the pipeline loop produce a result every nanoseconds instead of every 7 nanoseconds. Okay, so it will be reduced from 7,000 to 1,006. So 7 times faster. Okay, so you can see from here, we have 7 steps, 1, 2, 3, 4, 5, 6, 7 steps. Okay, so you can see when you add here, you have 1,006 seconds. Okay, the first one will take time. Okay, but after that, it will generate every 1 nanosecond instead of every 7 nanoseconds. Okay. Okay, the other things is on the multiple issues. The pipeline improve performance by taking individual piece of hardware or functional unit and connecting them in sequence. But multiple issues processors replicate the functional units and try to simultaneously execute different instruction in the program. So for example, it is possible to halve the time to execute is even better, but remember that you need to have something like this. Okay, the program that can be divided from the data. Okay, that does not interact with each other. If you have some interaction with the previous one, then we cannot use this one. Okay, let's say something like this. Okay, instead of do pipelining, what will happen here? Okay, we do some addition here and this another addition. So while this one taking Z1, this one taking Z2, this one taking Z3, this one taking Z4, and so on. Okay, so at the end it will be faster by 2 times. Okay. Yeah, so while the first adder is computing Z0, Z1, and the other Z1, 2, and Z3. Okay, so this one I think should be not 1, and this is 2 and 3. Okay, I will modify later. Yeah. Okay, so if the functional units are scheduled at compile time, the multiple issue system is said to be static multiple issues. So especially if you are using the FPGA, for example, if the functional units are scheduled at runtime, the system is said to use dynamic multiple issues. Okay. In order to make use of multiple issues, the system must find instruction that can be executed simultaneously. So so we need to speculate. Okay, we need to predict. We need to make some prediction. Okay. So the processor make a guess about an instruction and then execute the instruction on the basis of the guess. Okay. This is the example. Z equal to X plus Y. I predict that it will be positive, so I run this one at the same time. Okay, but what if Z less than or equal to 0? Then the system speculate incorrectly. It must go back and recalculate W equal to Y. Okay. The other things, for example, like this, the system might predict that the AP does not refer to Z here. It does not depend on here. So it means that you can because this is the same different variable, so you can execute this in parallel. Okay, and I think now the compiler is intelligent enough to make a prediction. Okay, so that it will run faster. Okay, the optimization will make the run faster. Okay, so the let's see now the hardware multi-threading. So we have here previously what the multiple issues. We have pipelining, multiple issues. Okay, then we can see here the hardware multi-threading. Okay, so this is also called hyper-threading in Intel. Okay, it's devised by Intel processors, so it means it can run 2 instructions at once. Okay, the instruction level parallelism can be very difficult to exploit. It is a program with a long sequence of dependent statement offer a few opportunities. So, for example, like this. For in here, there is essentially no opportunities for simultaneous execution of instruction like this. Okay, because it depends from previous one. Okay, so the thread level parallelism provide parallelism through the simultaneous execution of different threads. Okay, so what if we cannot divide this one? Then we can run another program, different program. Okay, let me finish a bit here. Okay, so the thread level parallelisms provide a coarser grain parallel compared to the instruction level parallelisms. Okay, so instruction level, the thread level means you can run two programs at the same time. Okay, so for example, I can run one in it requires a bigger, for example, one Photoshop, one is Microsoft Word, for example. Okay, so the hardware multithreading provide a mean for system to continue doing useful work when the tasks are being currently executed has stalled. Okay, so for example, you can switch to another data and so on. Okay. So the hardware multi-threading, you can have fine grain as well. So switch between threads after each instructions and skipping threads that are stalled. The advantage is the avoid machine time due to stall, but the disadvantage is that a thread that is ready to execute along sequence of instruction may have to wait, okay, to execute every instruction. On the grain, only switch threads that are stalled, waiting for a time-consuming operation to complete. So the advantage is switching thread does not need to be nearly instantaneous, okay, because you are coarser grain, but the processor can be idled on shorter stalls, and thread switching will also cause some delays, okay. And simultaneous multi-threading, the last one, is a variation of fine-grained multi-threading. So it allows multiple threads to make use of the multiple functional unit. Okay. Right. So I think I will stop here first, then I will continue on the next one, inshallah. Okay.